Okay, so by now you should have understood a little bit more about acids and bases, the fundamentals, the different definitions of acid or bases, and you should have an understanding of pKa value and how we can use pKa to measure the intensity of an acid, the strength of an acid. What we're now going to look at is how we can link that to pharmacy, how we can think about the different molecules that will come across, the different functional groups and the different bonding, and how those features can influence acidity. So let's remind ourselves about the equilibrium involved in acidity. So if we take an acid in the presence of water, there is this equilibrium in which we will lose a proton from HA and we end up with A minus. Remember that we have this equilibrium constant here. So when we're looking at how strong an acid is, one of the key things we're looking at is this species here, this anion A. And what we want to be able to do is to stabilize it. Okay, so that the more stable A minus is, the more the stronger the acid will become. So the question is, how can we stabilize A minus? Well, there are a number of different things we can do, and so we're going to have a look through several of them. We're going to look at how the electronegativity difference between H and A can influence that acidity. We're also going to look at things like the size of the atoms, inductive effects, how the electron distribution in a molecule will affect the strength of or the stability of A minus, and equally how the hybridization status of the atom can affect it. And then finally we'll look at some resonance or delocalization effects. So electronegativity is one of the first things we consider. If we think we've already looked at electronegativity and we understand that there are different electronegativities for different atoms, one of the key ones to look at is the difference between a hydrogen and a halogen. So HCl as a classical strong acid, what will happen here is we will end up with H plus and Cl minus. And what we know in HCl is that we have a delta positive hydrogen and we have a delta negative chlorine. So the chlorine atom in HCl already has this additional level of minus charge due to its electronegativity. Very electronegative, is drawing the electrons through this bond towards itself to give that positive charge on the hydrogen and delta negative charge on the chlorine. So it's very simple then to break that HCl bond because the electrons actually reside more closely on the chlorine atom than they do on the hydrogen atom. So chlorine, being this very electronegative atom, is very, very comfortable having extra electrons. So to have that extra electron and to have that minus charge, because of its electronegativity, it's actually very, very stable. So when we look at the differences in electronegativity, that's what we're thinking about. We're thinking about how do we draw the electrons away from the proton, which will mean that the resulting anion will be a more stable one. So next we're going to look at what we would call, I guess, bond energies, or more appropriately, we're looking at atom size in this case. So when we're thinking of atom size, what we're interested in is if we go back to our hydrogen attached to a halogen, so if we took something like HF, what we know if we look at the pKa values of this is HF has a pKa value of approximately 3, okay, and HI, so iodine rather than fluorine, this has a pKa value at minus 10. So what that tells us is that HI is a much stronger acid than HF. So why would that be? The only difference is in these halogens, and in actual fact, if we look at those halogens, we find that iodine is actually less electronegative than fluorine. So based on what we've just discussed about electronegativity, we'd expect this to be the other way around. But remember, what we're interested in is how can we stabilize the anion? So we have F minus and we have I minus. And this is where atom size becomes important. So if we think that minus charge, it's going to sit in our atom. And if we have our fluorine here, we have a relatively small atom. So you have the nucleus here, and we have a relatively small atom. So the minus charge has to fit in this quite small, tightly confined space. Whereas if we look at the iodine is a much larger atom. And so that negative charge can be distributed within those orbitals, much larger orbitals, so they are more diffuse. And because they're more diffuse, they're not these kind of very focused point charges. And that diffusion of the extra electrons within a much wider electron cloud space in those orbitals gives it a much more stable structure. We can see the same thing not just in halogens. If we take, for example, something like an alcohol, so ROH, that would give us RO minus plus H plus. Okay, or we could look at the sulfur derivative of that, so RSH, and that would end up giving us RS minus plus H plus. And exactly the same thing happens here. If we look at the oxygen is a smaller atom to if we look at the sulfur. So the sulfur is a much bigger space. And so when we look at those, the difference between an alcohol and a thiol, the thiol, for example, has a pKa. This is the methane derivative of 10.5, and the alcohol, so methanol, has a pKa of 16. So we can see that the sulfur derivative is actually a stronger acid than the oxygen derivative, and that's because in that anion here, this RS minus, the negative charge is distributed within a much larger orbital space. So we've considered the effect of the atom that the negative charge actually sits on, but what about any other bonds that that atom may have? So let's just create our new hypothetical acid. Okay, and this is going to dissociate to give us Xa minus plus H plus. Okay, and so what we're interested in now is, well, what about the stability here of the Xa minus? Well, if we were to introduce, we know that the stability of that negative charge is the key. So if we have a very strong negative charge, we need some way of stabilizing it for Xa minus to be favorable. And we can do that by, if X is some kind of electron withdrawing group, and we'll explain the kind of thing that I mean in a minute. So what that would mean is if Xa minus, what an electron withdrawing group, it would pull the electrons, that negative charge would be pulled towards the X. So this would be favorable. If we had something which was electron donating, in which case this X pushes electron density towards the minus charge, this would have a destabilizing effect on that A minus. So the electron withdrawing group would help to stabilize the acid, and an electron donating group would destabilize the acid and make it less favorable. So let's look at some examples of that. So if we take, for example, a carboxylic acid, what's going to happen in the carboxylic acid is we're going to form O minus here plus H plus, and the pKa of this is approximately 4.8. Okay, if we take the same thing but we add a chlorine atom here, okay, we are going to form that same kind of anion plus a proton, but in this case the pKa is 2.9. And the reason that this happens is as we get to this negative charge on this anion, the chlorine is very electronegative, as we said, so it's going to be drawing any free electrons towards itself. And it can do that through the sigma bond slightly. So what we're effectively doing is we're taking this lone pair of electron, or this negative charge, and we're slowly moving it through the sigma bonds, through those orbitals. Not completely, but just a small amount of it, just enough that means that this negative charge here, so this, becomes more stable than in this example. And so therefore, because that negative charge is more stable, the anion is more stable, the equilibrium moves more towards the anion and the H+, and so we have a stronger acid, so we have a lower pKa value. So if an electron withdrawing group is favourable, how is an electron donating group unfavourable? Well, again, let's take the same kind of example. So we take our carboxylic acid, which we had before. We know we're going to form this anion and a proton, and we know that this has a pKa of 4.8. Well, a methyl group is considered an electron donating group. Professor Osborne spoke to you a little bit about stabilization of carbocations. We know that it can push electrons into a space. So we know that this methyl group will push electrons through. So what happens if we take the methyl group away? Okay, we will form this oxygen anion again, plus H+, and in this case, our pKa value drops down to 3.7. So again, if we take this anion here, okay, and we think about what does this mean? Well, we have this carbon, we have these hydrogens, and we know from the material that Professor Osborne gave you that we can use carbons to push electron density into stabilized carbocations. We can do the same thing here, but we're pushing the electron density in this way, okay, which ultimately has the effect of pushing more electrons towards this negative charge. So that negative charge becomes more charged, and that is unfavourable. So whereas before in the electron withdrawing group we were taking the electron charge and spreading it out within the molecule, here we're actually pushing more electrons towards that charge, which makes it less favourable and less stable, and so therefore not as strong an acid. So when we look at these two pKa values, we see that the methyl carboxylic acid here with the methyl group is not as good an acid because of that pushing in than if you just have the hydrogen there. Acidity can also be affected by the hybridization of the atoms that the negative charge is on. So if we take sp2 and sp3 hybridized carbon atoms as the example to work through. So if we start with our sp3 hybridized atoms, so we have something like ethane, and if we were to look at turning this into an anion, okay, we would end up with sp3 hybridized and empty, or an sp3 hybridized orbital with this pair of electrons in, okay, plus our H+. So this is our anion. So here is our anion with the electrons there. This is sp3 hybridized, and this has a pKa of 50. Okay, and then if we look at the next one, which would be sp2 hybridized, so if we looked at a alkene, we look at if that was to dissociate, what do we end up with here? Same thing, we've got this sp2 hybridized orbital this time, and this has a pKa of 44. So why is it that the sp2 hybridized carbon would be a stronger acid than the sp3 hybridized carbon? Well, it all goes down to in this case, how close the electron is to the positive nucleus of the atom. So if we think that, if we go back to hybridization from Dr. Ullmann, we know that the sp3 comes about because there is, one s orbital and 3 p orbitals making up that molecular orbital, whereas the sp2 has got the one s orbital and 2 p orbitals making up the molecular hybrid orbital. So the s orbitals are closer to the center of the nucleus than the p orbitals, and so in an sp2 hybridized orbital, it has more s character. So the shape of that orbital means that it is closer to the center of the atom, the nucleus of that, which is positively charged, and so of course the negative charge of that extra electron is stabilized by the positive charge or the positive nature in the center of the atom. So therefore, by being closer in that orbital, it can help to stabilize it. If all the other things are the same, if we go back to previously, we were looking at atom size, the bigger the atom there, the more diffuse the electron can be. But in this case, we're talking about carbon atoms. The orbitals are the same size in this case, but in there, getting it closer to the center, to the nucleus, actually helps to stabilize. So what would happen if we looked at the final one, which would be a alkyne, where we've got the triple bond? If we dissociate that, we would end up with this sp orbital, and following this pattern, that's got more s character than the sp2, so therefore we would expect the pKa to be lower, we would expect it to be more acidic, and in actual fact we find out that the pKa here is 25. So what we can say is that the more s character we have, the closer that electron, that extra electron in the anion, can be to the positive nature of the center, the nucleus of the atom, and therefore the more stabilized it can become, and therefore the more acidic it can become. So the final one that we would need to look at would be resonance and delocalization. But before we can look at how resonance and delocalization affect acidity, we just need to go back and remind ourselves of what resonance and delocalization is. So we're going to go have a look at that, and then we'll come back to finish off what is the feature of resonance and delocalization that affects acidity. So let's remind ourselves what we mean by delocalization and how we use resonance structures to show the impact of a delocalized system. So if we start with drawing a double bond, okay, what we remember with a double bond is we have a sigma bond and a pi bond, and the pi bond is formed by electrons in the p orbitals, which have this kind of electron overlap here. So if we draw that out again, okay, so we have our double bond, but this time we have a second double bond. So if we draw in our p orbitals, and we have our orbital overlap here, we draw in our p orbitals, and we have our orbital overlap here. Now what you can see from drawing in these orbitals and from this diagram is we have the distance between the two p orbitals that we have drawn in here, but we also have two p orbitals together here. So what stops us from saying, well, could that not be the double bond? And the answer is yes, it can be. So when we talk about delocalization, what we mean is that the electrons in these pi orbitals can actually delocalize, be spread amongst all four of the p orbitals here. So we don't have necessarily these fixed double bonds. It's more like the double bond character spreads across the whole molecule. So this is, I guess, the equivalent of saying we have this molecule. Okay, so that's what we mean when we talk about a delocalized system, and hopefully you can see in a minute that obviously we're talking about the stabilization of the charges that occur, stabilization of the anion of the negative charge. And so if we can spread that negative charge across more atoms, it can be more stable. So having a delocalized system will affect the acidity of the system. Another example, just to remind ourselves where we've seen this kind of delocalization before, is if we were to consider making a carbocation here, what we can do is we can draw what's called a resonance structure. So we can show that the electrons in the double bond could actually move into this bond here. So what we actually do is move that positive charge between the two carbon atoms. And we could do the same thing with a negative charge. So if we had a negative charge here, this double-headed arrow represents a resonance structure. We can draw, sorry, that's the wrong way around there. We can draw the electrons moving to move that negative charge across multiple atoms. So delocalization is the fact that the electrons can move within those p orbitals and be spread across multiple atoms. We're going to see that much more when we start looking at the aromatic chemistry. And the resonance means that we can draw these resonance structures. So where we put in this kind of double headed arrow to show that the electrons can move within that molecule and show where the charge is and where the electron distribution is. So what we'll look at next is how does this resonance, this delocalization, actually affect the acidity of a molecule. So let's start with another molecule. So here we've just got a simple alcohol, and this can exist in an equilibrium where we can deprotonate the alcohol to give us our anion plus our proton. So this is acting as an acid, and in this case the pKa of this is 16. If we go back to the molecule that we've been looking at before, our carboxylic acid, again we can show that this can dissociate to give O- plus H plus, and we've already seen that this has a pKa of 4.8. So we can tell from the pKa that the carboxylic acid is the more acidic of these two species, and if we think about resonance and delocalization, we can understand why. So we've said all along that stabilizing the anion, so stabilizing this, will help to make it more acidic. If the charge that we form, the anion that we form, is more stable, then it's more happy to give up that proton, and therefore it's more acidic. So we can show that we can draw resonance structure. So we can take this minus charge, this negative charge, we can move a pair of electrons to form a new double bond between the oxygen and the carbon, and then we can break this carbon-oxygen double bond to form a resonance structure. So what that will do is it will put the negative charge up the top here and neutralize it down the bottom. So we have been able to spread that negative charge across multiple atoms. So if you think this is kind of the equivalent to saying that the oxygen is up here, the oxygen down here, and we've got this kind of negative species, that charge is spread across those multiple oxygen atoms. And that helps us to see how this ability to have resonance, this ability to move that charge throughout the molecule, will help to decide whether it's more or less acidic. We'll also see resonance in far more detail when we start looking at the aromatic chemistry. So if you want to read any more about what I've just discussed, the best place to look at is chapter 4 in the book by Dewick, The Essentials of Organic Chemistry for Students of Pharmacy, Medicinal Chemistry and Biological Chemistry. You'll see that I've just taken the key points and explained those to you. In that chapter, it goes into a little bit more detail about the factors that influence acidity, and gives lots more examples. And what I've done is just pick one example to show you how these different factors may influence acidity.